Swayam Prabha. Digital India. Educated India.
Welcome to the next lecture on 3D printing processes. So 3D, it talks about the dimension of the object which we are going to do, and we are going to use the technology what we use in printing. Currently almost every house has a desktop printer, wherein which what we print is 2D laminate information in one sheet paper. So we are going to use that technique and we are going to develop 3-dimensional objects. So that is what is discussed in this process, 3D printing processes. And by the way, I reiterate, all these things are focused towards rapid manufacturing today. We are not talking about prototyping. This technique, whatever gets developed or the product which is get developed, this can be used as a mold, or it can be used to make a die from which you can get a product. So all these techniques are used only for that. In this lecture, we will try to cover 3D printing, in 3D printing technology, advantages and technical challenges which are available today. Then there is another technique which is called as droplet formation technologies, wherein which there is a continuous mode, drop on demand mode, other droplet formation methods. Then we have printing processes modeling, then material modification, binder printing, and last we will see fused deposition modeling. Introduction. Printing technology has been extensively investigated, with the majority of the investigation historically based upon applications to the two-dimensional printing industry. Recently, it has spread to numerous new application areas, including electronic packaging, optics, additive manufacturing. Printing technology. Today we have started printing electronic circuits on shirts, printing images which can change color. Printing technology has got so advanced. Some of these applications in fact have literally taken the technology into a new dimension. That is true. Today we have flexible electronics, wherein which printing technology is exhaustively used. Now started making printing optics. And then additive manufacturing is one big area where printing technology is exhaustively used. The employment of printing technologies in the creation of 3-dimensional products have quickly become an extremely promising manufacturing practice, both widely studied and increasingly widely used. It is not in research, it has already come to the application. The development of printing as a process to fabricate 3D parts is summarized, followed by a survey of commercial polymer printing machines. Both direct part printing and binder printing technology, direct part printing and binding technology are introduced. Direct part means whatever you get will be the direct product. Here we will try to bind the building materials and use that as a technology to develop a 3D product. Direct printing refers to processes where all the part material is dispensed from a printing head, while binder printing refers to a broad class of process where binder or other additive is printed. So here where all the part material is dispensed through a printing head in the direct part printing. When we talk about binder part, the building block is not dispensed, but the binder is dispensed, through which we try to develop a 3D part. Some of the technical challenges of printing are introduced. Material development for printing polymer. metals, ceramics is investigated in some details. From the topic of pure printing technologies, we move to three-dimensional binder printing process where binder is printed into a powder bed to form a part. See, why printing technology is very well talked about is because it is a well established process. And it can be mass produced, and so it is economical. So that is why printing technologies are exhaustively used, and printing technologies over a period of time has got so much of nascent knowledge which can be taken to the other fields and which can be used. Today we use bioprinting. Today we talk about printing of cloth, wherein which in that cloth wherever you print metal, and these metals are functionalized, and those functionalized metal printing on cloth is used as a sensor. So printing technology is fabulously going high in their level. So through optical fibers we have now started weaving shirts, and through this optical fiber, when light is passed through, it generates different colors. So printing technology has been evolving over a period of time. Today we talk about tissue printing, and we are talking about organ printing. So printing technology has gone to such a high level. And here, so when I say technology, it's not the machinery alone, the raw material, the quality check, and the consistency in the product. All these things have got enhanced. So that is why printing technology is now adapted in additive manufacturing or rapid manufacturing. Once the layer is printed, the powder bed is lowered. It's just like your SLS process, and a new layer of powder is spread on it, very similar to a recoating method used in powder bed fusion process. The process is repeated until the part or the array of parts is completed. Till now I did not talk about this array of parts. So in a single bed you can make multiple parts growing simultaneously. So this is where we are now talking about rapid prototyping to rapid manufacturing. So you have optimized the space and you have placed the part what is to be printed in such a manner such that you can get 4 or 6 or 10 in one shot. Okay. An array of parts is completed because the printing head contains several ejection nozzles, 3D printing features several parallel one-dimension avenues for patterning. So this is how a typical schematic diagram looks like. You have a powder spreader, so that spreads on top of the table. So the table will have a tank. So this is the table. This is the actuation or a lead screw which moves back and forth, up and down. And so here the powder, when it is spread on top of it, so one layer thickness is maintained, and then we use the inkjet printing head which is attached to a frame which can move in x and y direction, and the inkjet drops the binder on top of the powder. So now the powder gets agglomerated. So between this you have a binder which falls. So it need not be exactly. So the binder can fall on top of it and also connect the powder parts, which is a building block. So the powder is spread on top of the table. One layer thickness is done. So now the inkjet head, which can move in x and y direction, moves, and then the binder is dropped at exact locations where the part has to be built. Now the part is getting built, and finally the part is called as a green part because the binder might not have very high strength. After this, the part can be immersed inside of another polymer, varnish or something like that, so that the outer core layer is stiffened. Okay. So here the part need not have very high strength. It is only to give a form, shape by this process. Okay. After this, you can use this as a pattern for making a mold to a component, etc., etc. Since the process can be economically scaled by simply increasing the number of print nozzles, the process is considered a line-wise patterning process. Such embodiments typically have a high deposition speed at a relatively low cost, because the technology is already known, which is the case for 3D machines. The printed part is typically left in the powder bed after its completion in order for the binder to fully set and for the green part to gain strength. So, after this you remove the part, you can put it for post processing, you can put it for an annealing temperature. This annealing temperature has to be relative with respect to that of the binder which is used. So, do not think of very high temperatures, very low temperatures, it will be kept for annealing, so that the binder all properly joins, melts and adheres with the powder. The post processing involves removing the part from the powder bed, removing unbonded powder via pressurized air. So, whatever powder was available, so now you put a vacuum suck, this is a vacuum cleaner, vacuum cleaner. So, this just cleans and sucks all the loose powders and it is taken back. Now, that is reused and fed into the tank of the powder spreader. Pressurized air and infiltrating the part with the infiltrant to make it stronger and possibly to impart other mechanical properties. The 3D process shares many of the same advantages of powder bed processes. Parts are self-supporting in the powder bed, so that the supporting structure are not needed. And interestingly, if you want to add color to your binder, color plus binder, you might get a colorful object. The building block can be, the powder can be white in color. When you try to mix color to the binder, so again this concept you can always visualize with respect to 3D printing, inkjet printing. So, you have 3 colors, the 3 cartridges are filled with different colors, and what you get a printout is multicolor printout. So, like that you can control the color, add it to the binder, and the binder, when it drops on top of a powder which is white in color, you get different colors. For example, if you want to give a 3-dimensional topological mapping of a hill region, so you can always very clearly say where are the land, where is green, where is a patch, where is water running, everything can be taken a printout using this 3D printing. So, it is very good. Okay. So, the 3D printing process shares many of the same advantages of powder bed processes. Parts are self-supporting in the powder bed, so that the supporting structures are not needed. Similar to other processes, part can be arrayed in one layer and stacked in the powder bed to greatly increase the number of parts that can be built at one time. Finally, assemblies of the parts and kinematic joints can be fabricated, since loose powder can be removed between the parts. Okay. So, this is very important. So, what we are trying to say is, suppose you want to make a big part, so then the big part, because of the size restriction of the table, you are not able to make. So, then the other easiest way of making it is, you make them into several small pieces, and at every piece you try to have a female and a male part, so that once the part is made, you remove the part and attach it and attach male and female together, so that you get the required output. That is what we are trying to say. The other way around, you can make multiple array of parts in one shot and start printing it. So, this is what is discussed in this point. So, each rapid manufacturing process has its advantage and disadvantage. The primary advantage of printing both direct and binder printing as an RM process includes low cost, high speed, scalability, ease for building parts in multiple materials, and the capability of printing color. So, all these things are possible in 3D printing, which gives it a major edge over the others. When you use laser, you can generate this color, but here you can easily generate the color because you are mixing it with the binder. The printing machines are much lower in cost than the other RM process, particularly the ones that laser use. In general, printing machines can be assembled from standard components, driver. So, there are drivers. When you talk about drivers, there are two drivers, as I told you earlier, it is belt, the another one is lead screw. Then stages, then you have printing heads. So, these are some of the building components which are already available commercially in the market. So, all you have to do is you do your shopping, pick it up, online shopping, pick up all those things to your requirement, and then start customizing to get the required specification in your 3D printing, while other machines have more machine specific components. High speed and scalability are related. By using printing head with hundreds or thousands of nozzles, it is possible, whereas when you do a extrusion process, it is only one nozzle. So, here you can have hundreds of nozzles. It is possible to deposit a lot of material quickly and over a considerable area. Scalability in this context means that printing speed can be increased by adding another printing head to the machine. A relatively easy task, much easier than adding another laser in SL process or SLS process machines. Related to multiple material, color can be printed by the same AM material. The capability of printing in color is an important advantage in the AM industry using 3D printing. The only exception was the selectively colorable SL resin that Hudson machine marketed for the medical industry, which were developed in the mid 1990s. These resins were capable of only two colors, amber and either blue or red. So, these are the colors which it could do, but here you could have any number of colors you want. For binder printing, some polymer, ceramic composites and metals are available, but they come with many limitations. Part accuracy, particularly for large parts, is generally not as good as with some other processes, notably SL or fused deposition modeling. This is one of the disadvantages. However, accuracies have been improved across the industries and are expected to improve among all other processes. What are the big technical challenges? So, as evidenced by the industry and research application of printing discussed in the previous section, printing already has a strong foothold in terms of becoming a successful RM technology. There are, however, some serious technical shortcomings that have prevented its development for further growth. To identify and address those problems, the relevant phenomena and strategic approach taken by its developers must be understood. Printing for three-dimensional fabrication is an extremely complex process with challenging technical issues throughout. The first challenge is, if the material is not in liquid form to begin with, this may mean suspending particles in a carrier fluid, dissolving materials in a solvent, melting a solid powder, or mixing a formulation of monomer or pre-polymer with a polymerization initiator. Formation is a big challenge in printing. So, the binder becomes a big challenge. If the material is not in liquid form, then you have a big challenge, binder material. In many cases, other substances such as surfactants are added to the liquid to attain acceptable characteristics. Now, you see a surfactant is there, liquid metal is there, then you have a building material. So, all the three will have different wetting properties, they will have different temperatures required for adhering. So, all those things bring us, it makes multi-physics interaction, or understanding the process needs multi-physics approach. Entire industry are devoted to the mixing of ink for two-dimensional printing, and it is reasonable to assume that in the future this will also be the case for three-dimensional fabrication. The second hurdle to overcome this droplet formation, to use inkjet deposition method, the material must be converted from a continuous volume of liquid into number of small discrete droplets. This is also a big challenge. You have a flow of liquid, there is a flow of liquid. So, this flow of liquid has to be now converted into droplets, which is a huge challenge. So, you have to reduce the flow. When you reduce the flow, there will be lot of surface dominated friction. So, this will not allow the liquid to flow so easily. So, you have to pressurize it and then take it out. When you take it out, again the droplet size should be uniform, and this droplet should not get joined to each other. So, once it joins, when it is getting dispensed, it will not be uniform. And when we are trying to move this binder head on top of the powder bed, if there is a air bubble which is getting stuck while flowing, then that portion there will be a defect which is getting created. And when you burn it or keep the post processing process, when you anneal it, there starts a defect from that process. So, here this is a big challenge. You have to understand the fluid flow through micro channel and getting dispersed into small droplets. The droplet size plays a very important role. If the droplet size is large, then unnecessarily lot of binder will be used. If the droplet size is small, it has to be synchronized with the feed rate. If that is not done, it is prone for defects. Okay. This function is often dependent on a finely tuned relationship between the material being printed, the hardware involved, and the process parameter. A number of methods of achieving droplet formation are discussed in the forthcoming slides. Small change of the material, such as the addition of tiny particles, may drastically change its droplet formation behavior as well, as can change to the physical setup. So, in this droplet, if you have nanoparticles dispersed, then this becomes a different ball game completely to operate. A third challenge is controlled to the deposition of this droplet. This involves issues of droplet flight path, impact, and substrate wetting or interaction. When the droplet falls from a certain height, how does it fall and how does it interact? In printing process, either the printing head or the substrate is usually moving. So, the calculation of the trajectory of the droplets must take this issue into account. Okay. Because the droplet is falling, it is like your plane dropping a bomb. So, a droplet is forming and parallelly this head is moving. Head, droplet. Okay. Droplet falling down, head moving. So, what will happen is there will be a flight path. So, this will, instead of falling like this, it might take a path like this. So, we have to be careful. In printing process, either the printing head or the substrate is usually moving. So, the calculation of the trajectory of the droplet must take this issue into account. Otherwise, what will happen? You will keep moving and the droplet will not fall, it will jump and you will not get adhesions. In addition to the location of the droplet arrival, droplet velocity and size, the droplet size is very important and the droplet velocity is also important. It is very complicated issue when you start modeling it, and once you do not model, you will not be able to do experiments and find out the range with which it is done. Otherwise, you will keep doing experiments umpty number of times. So, you should have a ballpark feel such that you can try to convert a liquid flow into droplets and droplet size control. How do they control the droplet size? They at the exit they have a piezo crystal. The opening on the piezo crystal happens so fast and the droplets are formed and it is allowed to drop. And if the droplet which is formed is too small and in the flight movement, when the binder head is moving, this droplet will just ooze out and it will fly in air. So, you have to be very careful. So, this is a huge challenge. Binder, formation of the binder, if it is not a liquid, huge challenge. Second thing is, if it is liquid, how to convert it into droplets is a challenge. Third thing, dropping these liquids is also a challenge. So, we have three big challenges in front of us when we talk about these 3D printing. The quality of impact droplet must also be controlled. If the small droplet called satellite breaks off from the main droplet during flight, then the deposition material will be spread over a large area than intended area and the deposition will not have a well defined boundary. Very interesting. So, when it falls down, suppose if it stays here, it is good. When it falls down and if it does not stay, it jumps because of weight or because of the volume of the material. It just drops and it shatters. When it shatters in the other area. Suppose if the path is like this, it shatters here, it shatters here. So, this is the boundary condition of the information in one layer. So, if it shatters, now this layer also will get stuck to it. Now, you see, instead of getting a precise external boundary condition, you will have a large, thicker boundary condition. This is a challenge to be controlled. In the same way, if the droplet splashes on impact, forming what is called the crown, similar results will occur. All of the effects will negatively impact the printing quality of the printed material. These three challenges puts a major restriction of using this technique for printing feature size which is very small and having very high resolutions. So, there is lot of work going on to improvise, to play with the viscosity of the binder and then the droplet formation, dispersion and all those things. Concurrently, the conversion of a liquid material droplet to a solid geometry must be carefully controlled. Direct printing relies on a phase change of printed material. Example of phase change mode employed in existing printing technologies are solidification of a melted material. For example, they would like to drop wax and go, they would like to drop solder paste and go. So, solidification happens. Evaporation of liquid portion of a solution. So, what happens? There is a ceramic, there is a liquid melt. When it is exposed to the atmosphere, it evaporates, volatile material. So, evaporation of liquid portion of a solution happens. Then curing of photopolymer or other chemical reactions can also happen. So, these object and project machines follow this curing of a photopolymer by chemical reactions. The phase change must occur either during droplet formation or some soon after impact. Phase change, either exiting out of the tube and falling on top of the bed, before that there has to be a phase change, or once it falls down it has to have a phase change. The time and place of this conversion will also affect the droplet interaction with the substrate and final deposition creation. So, this is a major challenge in front of 3D printing. To further complicate the matter, drops may solidify non-uniformly, creating warpage and other undesirable results. In direct printing, an additional challenge arises that the controlling deposition a top layer of previous deposition rather than only upon the initial substrate. The droplet will interact differently, for example, with a metal plate substrate than with surface of previously printed wax droplet. To create substantive three-dimensional parts, each layer deposited must be fully bound to the previous layer to prevent delamination, but must not damage the layer while being created. So, this is also a major challenge. While creating a 3D part, each layer deposit must be fully bonded to the previous layer to prevent delamination. So, as we told, this is delamination. Commercially available machines tend to approach this problem by employing devices that plane or otherwise smooth the surface periodically. So, you have a knife or a sharp objects to smoothen the surface. Operational consideration also pose a challenge in process planning of printing. For example, because nozzles are so small, they often clog, preventing droplet to exit. Much attention has been given to monitor and maintain nozzle performance during the operation. Most machines which are currently in use go through a purge and cleaning cycle during the building to keep as many nozzles open as possible. They may also wipe the nozzle periodically. So, what they do is they stop, they have something like a dressing cycle, they will have a cleaning cycle, they have a purging cycle. While the component is made, the head will move out of the table completely, it will try to purge, it will try to clean after 10 minutes or 100 layers, and then it will come back and start doing it. So, this is becoming an inbuilt feature in these machines. Some machines may also employ complex sensing systems to identify and compensate for malfunctioning. In addition, many machines include all commercial RM machines have replaceable nozzles in case of permanent blockage. So, suppose if there are a array of nozzles, now the system is built in such a manner that you can replace every nozzle as and when it is done. Finally, to achieve the best printing resolution, it is advantageous to produce many small droplets very close to the dimensions. Droplet formation technology. Over the time, the two-dimensional inkjet printing has evolved. A number of methods for creating and expelling droplets have been developed. The main distinction in categorizing the most common of technologies refer to the possible mode of expulsion. One is continuous stream, another one is drop on demand DOD. This distinction refers to the form in which the liquid exits the nozzle as either a continuous column of liquid or a discrete droplet. Continuous mode. There are two modes, drop on demand, continuous mode. We are seeing continuous mode. The continuous mode, a steady pressure is applied to the fluid reservoir, causing a pressurized volume of the fluid to be ejected from the nozzle. After departing the nozzle, the stream breaks into droplets because due to Rayleigh instability. Stream breaks into droplets because of Rayleigh instability. The breakup can be made more consistent by vibrating, perturbating or modulating the jet at a fixed frequency close to the spontaneous droplet formation rate, in which case the droplet formation process is synchronized with the forced vibration and ink droplets of uniform mass are ejected. Very important point, and lot of research is going in this area. Very important point. So, a stream breaks into droplet due to Rayleigh instability. Then you can also vibrate, perturbate and modulate the jet at a fixed frequency close to the spontaneous droplet formation. So, let me draw a small schematic diagram of continuous mode. So, schematic diagram. You have alternative layers. So, you will have here so this is the dispersed phase channel. This is alternating plug formation in the micro channel. This will be dispersed phase inlet 2. This will be dispersed phase inlet 1, and if I try to draw a line, this angle theta is the angle of taper alpha. This is a schematic diagram of the droplet generation device. This is a schematic diagram of the droplet generating device. So, you have a dispersing phase inlet 1 and you have a dispersing phase inlet 2, right. So, these two phases they try to eject. So, you can see alternative of the dispersion phase. So, this is phase 1 and this is inlet phase 1 and this is phase 2. So, you see how it is the continuous droplet phase. So, this the continuous phase inlet and the two phase dispersion inlets are shown here. Okay, the angle of taper is denoted by alpha. Because the droplets are produced at constant intervals, their deposition must be controlled after they separate from the jet. To achieve this, they are introduced to a charging field. Okay. At the exit, there is a charging field and thus attain an electrostatic charge. These charged particles then pass through a deflection field which directs the particles to their desired destination, either a location on the substrate or a container of material to be recycled or deposited. So, that is how you break a continuous one into discrete parts and discrete droplets, and then this discrete droplets is allowed to fall. An advantage of CS deposition is the high throughput rate. It has therefore seen widespread use in applications such as food and pharmaceutical labeling. There we use this CS deposition. Two major constraints related to this method of droplet formation are, however, that the material must be able to carry a charge and that the fluid deflected into the catcher must be either disposed of or reprocessed, causing problem in cases where the fluid is costly or where waste management is an issue. So, these are the two major constraints related to the droplet formation: to carry a charge and that the fluid deflection into the catcher must be either disposed or reprocessed. Few investigators of three-dimensional deposition have opted to use continuous printing method. Drop on demand mode. In drop on demand mode, in contrast, individual droplets are produced directly from the nozzle. Droplets are formed only when individual pressure pulses in the nozzle causes the fluid to expel. In the previous one it was not so. So, it was a fluid coming, you applied a electrical charge field, the droplet came. But here you will pressurize such that individual pulses get expelled out. These pressure pulses are created at specific time by thermal, electrostatic, piezoelectric, acoustic or other actuators. Generally in our printers we use piezoelectric. This is well established and well controllable, so we go for piezoelectric. In the current DOD printing industry, thermal and piezoelectric actuator technologies dominate. These are shown in the next slides. The thermal actuators rely on the resistor of heating. Heating is I square RT, Joule heating effect, right. The liquid within a reservoir until a bubble expands in it, forcing a droplet out of the nozzle. So, you can see here thermal and piezo. These are piezo, crystal is there. So, heater is applied, there is a ink. So, there is an orifice. When it is heated, this gets heated up and this pushes the ink through the orifice, and when the weight is more, when the weight of the droplet size is whatever equal or slightly more than the orifice diameter, it tries to droop off from the tank. Till that time heating is used. The other way around, we try to use a piezo crystal, piezo ceramic. So, piezo ceramic is you activate it, you apply a voltage, it has a displacement, this displacement pushes the ink. So, this ink pushes, so the orifice you have a droplet which is coming out, when there is more amount of displacement given, the droplet falls down and you get a fine droplet. So, this is on demand. Wherever there is a need, this is done. In the earlier one, it is continuously flown and then you have a droplet which is getting formed. So, two different technologies are used. Piezoelectric actuators rely upon the deformation of a piezo crystal element to reduce the volume of the liquid reservoir, which causes a droplet to be ejected. As noted by Basran, the waveform employed in piezoelectrically driven DOD system can vary from simple positive square wave to complex negative positive negative wave, in which the amplitude, duration and the other parameters are carefully modulated to create the droplet as desired. The preference for piezoelectrically driven DOD printing is reflected in the number of investigators who use and study such steps. Aside from the standard continuous mode and drop on demand method, other technologies have been experimentally investigated but have not enjoyed widespread use in the industries. There are other techniques, it is not only these two. Liquid spark jetting, a relative of thermal printing, relies on a electrical spark discharge instead of resistor to form a gas bubble in the reservoir. They have used that. The electro-hydrodynamic inkjet employs an extremely powerful electric field to pull a meniscus and under very specific condition droplet from a pressure controlled capillary tube. These droplets are significantly smaller than the tubes from which they emanate. The conservation of energy concept provides an appropriate content for investigating droplet generation mechanism for printing. So, this is the important point, droplet generation. Essentially, the energy imparted by the actuation method to the liquid must be sufficient to balance three requirements: fluid flow loss, surface energy, kinetic energy. Again, this point is very important. The energy balance will be done between fluid flow loss, surface energy and kinetic energy. The losses originate from a conservation of kinetic energy to thermal energy due to the viscosity of the fluid within the nozzle. This conversion can be thought of as a result in internal friction of the liquid. So, these are all techniques, but in the entire 3D printing technique, you should understand the binder which comes out, okay, that getting it into a droplet size is a big challenge. So, the fluid flow when printing are almost always lamellar, that is Reynolds number is less than 2100. As you know, Reynolds number Re depends on rho, V, R and mu. Mu is the dynamic viscosity of the liquid, rho is the liquid density, R is the tube radius, V is the flow velocity across the pipe. With this we calculate the Reynolds number. The Reynolds number, if it is less than 2100, it is called as a lamellar flow. The fluid flow will always be maintained at lamellar, because when you go to turbulent flow, it becomes a challenge. And the other thing you should understand, when we talk about all this Reynolds number, we talk about the radius of the tube. So, the radius of the tube, this all holds good when the tube is in millimeters. When you have a micro channel and through which the liquid has to flow and get dispersed, this will all be in microns. So, this is a big challenge. Another dimensionless number of relevance in printing is the Weber number, which describes the relative importance of a fluid's inertia compared with the surface tension. So, Weber number is the other thing. Again, Weber number VE is given by rho V square R by gamma. Several research groups have determined that the combination of Reynolds number and the Weber number is a particularly good indicator of the potential for successful printing of fluids. So, the condition which is called as printing indicator is this. So, you will have 1 which is less than or equal to Reynolds number, Weber number to the root of Weber number, which is equal to rho root of rho r gamma by mu, which is again 1 less than or equal to Re, Reynolds number, Weber number to the root, that is to the root half is root of Weber number is equal to root of rho r strain by mu, which is again lesser than or equal to 10. The earliest and the most often used solution to the problem of high viscosity is to heat the material until its viscosity drops to the acceptable point. A hot melt deposition has very specific requirement for the material property of what is printed. Many current applications have tuned to solution or dispersion based deposition. The most recent development in addressing the issue of viscosity is to use a pre-polymer in the fabrication of polymer parts. A wide range of materials have been developed for 3D printing. Printing into a metal powder bed was first demonstrated in early 1990s. Currently, investigation with ceramic materials are going on. The traditionally powder-based 3D printing of ceramics involves the selective printing of a binder over the bed of ceramic powder. The fabrication of ceramic parts follows a very similar process compared with the metal part. The green parts created by this process are subjected to a thermal decomposition prior to sintering to remove the polymer binding. After the binder burns out, the furnace temperature is increased until the ceramic sintering happens. Sometimes an infiltrant is used, that the reactant to form a ceramic binder. Another possibility is to infiltrate with metal to form a ceramic metal composites. So, this is a process of binder jetting. So, we have a liquid adhesion supply. This is a liquid printing head which is there. So, this is a powder bed. We have powder bed. This is a building platform. This is a powder bed, and this is a build part. Okay. The same like your SLS process, you will have a supply which comes here, and then here you will have a liquid adhesion supplying, and then inkjet printing head. So, liquid adhesion from here supplies to here, and then this fellow moves in XYZ direction, and you can start developing it. So, advantage of binder printing process shares many of the advantage of direct printing relative to the other RM process. With respect to the direct printing, binder printing has some distinct advantages. First, it can be faster since only a small fraction of the total part volume must be dispensed through the printing head. However, the need to recoat powder adds an extra step to the process. Second, the combination of powder material and additives in binder enables material composition that are not possible and not easily achievable with direct method. Third, slurries with higher solid loads are possible with binder printing compared with the direct printing, enabling better quality ceramics and metal powders. As mentioned earlier, binder printing process lend themselves readily to printing colors on top of parts. The last process of discussion is going to be fused deposition method. So, it is this process almost overlaps with that of your extrusion based process. So, here we need to have a supporting material. So, the supporting material is separately fed, the building material is separately fed. The tension in the extrusion process is maintained by these two spools or two rollers. They try to maintain the tension, and the filament comes from the spool, passes through a nozzle where it is heated, and then it is allowed to deposit on top of a table or a platform. The platform sinks down, so layer by layer information is built, and then you start getting the required output. So, in this chapter what we saw was 3D printing, what was droplet formation technology, about printing process modeling we saw, material modification methods we saw, and binder printing and fused deposition models we saw. Thank you.